It's my pleasure to speak in this seminar. And this work is a joint work with my student, Mitra Alizadeh. Okay, so it's first we call the Heisenberg group. The first Heisenberg group consists of all the up triangular matrices with ones on the diagonal. And it can be identified with R3 with the following group operation. So you have x, y, z, and x prime, y prime, z prime. The product is given by, so in the first two coordinates, that's the usual addition. In the third coordinate, in addition to z plus z prime, you have this term involving the coordinates from the first two coordinates. So it's half x y prime minus x prime y. In the Heisenberg group, okay, it's a new group, it's natural to consider left invariant matrix. So here we consider either left invariant Riemannian metric or left invariant Carnot-Theodori metric. There's also the discrete version of the Heisenberg group. So where the coordinates x, y, z are integers. So this is finally generated to the nilpotent group. We fix any finite generating set for this group. Then there's the corresponding order metric. So if the generating set is S, we denote the order metric by ds. Now the discrete Heisenberg group sits inside the Heisenberg group as a co-compact lattice. So it implies that the discrete Heisenberg group with the order metric and the Heisenberg group are quasi-isometric. So we're interested in quasi-isometries of the Heisenberg group. Let's first recall that the quasi-isometries of the Heisenberg group are quite flexible. So here I just recall some examples of quasi-isometries of the Heisenberg group. The first construction is given by sharing in the central direction. So recall we identify H with R3. Now, when we map H from R2 to R, we can define a map SH from the Heisenberg group to itself. So SH sends x, y, z to this point with coordinates x, y. So no change in the first two coordinates. In the z coordinate, there's the shear according to h. Okay, so z plus h x y. These maps are quasi-isometric if and only if there are constants L and C such that for only 2 points x1, x2 in R2, the absolute value between hx1 minus hx2 is bounded from above by L times the distance between x1 and x2 plus C. So if you see 0, then you just have a Lipschitz function. So you allow this additive constant C. So if you use the Maria's terminology, this is rough Lipschitz function. So for each rough Lipschitz function, you get the map you get S, which is a quasi-isometry. And this quasi-isometry is at bounded distance from an automorphism if and only if H is a bounded distance from a linear function. So if you pick H, a rough Lipschitz function, but it's not at boundary distance from any linear map. For example, you can take the absolute value function or the square root of the absolute value function. Then we get self-quasi-isometries of the Heisenberg group, which are not at finite distance from any automorphism. So this is one construction where you get some examples of quasi-isometry, which is shown in the central direction. The second construction is lifts of symplectic biapside maps of the plane. So you can see the two maps, lit F from R2 to itself, and another map, capital F from H to itself. We see capital F is a lift of lit F if you had commuting diagram. Lit F composed with pi equals pi composed with capital F, where pi is a projection from the Heisenberg group into the plane. So this is given by with the identification of H with R3, it's the usual projection from R3 to R2. Okay. So a result from 2006 by these three people, they showed that if lit F is Lipschitz, where the Jacobian is constant almost everywhere, then it emits a lift to a Lipschitz map from H to itself. And here, H is equipped with left invariant C-symmetric. So you can use this theorem to, construct mainly Lipschitz lift. If lit F is by Lipschitz, then the lift will be by Lipschitz map of the Heisenberg group H. So there exist exotic symplectic bi-Lipschitz maps of the plane, and their lifts to the Heisenberg group will give rise to exotic bi-Lipschitz maps of the Heisenberg group. So here's an example where the map lit F is not a product map, but it's differentials product maps. So there is a bi-Lipschitz map of the plane where the Jacobian is 1 almost everywhere, and with the following properties. So at each point x, the differential has one of the two forms. It's either diagonal, so that means the differential preserves x direction and y direction, or the other form, which is like this. So that means the differential sends x axis to y axis and sends y axis to x axis, switch the x direction and the y direction. But the map F itself is not a product map. So you have these bi-Lipschitz maps of the plane, and if you consider their lift to the Heisenberg group, you get some exotic bi-Lipschitz map of the Heisenberg group. So that's the second construction. It is to consider lifts of symplectic bi-Lipschitz maps of the plane. Third construction is to conjugate by the Colonian inversion. So identify the Heisenberg group with R3, which is identified with C cross R, and equip H with the C-symmetric. The Colonian inversion of the Heisenberg group is similar to the inversion in the unit sphere of R3, and there's formula given by okay, it has formula given by this. Now, so this sends the origin to infinity and infinity to origin. Okay. Now, if we start with any Valley-Pitts map F of the Heisenberg group H, which fix the origin, you can always arrange this by doing a left translation. Then its conjugation by the Coulomb inversion is again Valley-Pitts. So now you can start with any nice Valley-Pitts map F, and it can conjugate by the Coulomb inversion. And after so even if F has nice structures, its conjugation may not. So that's another way to get some Valley-Pitts map of the Heisenberg group. So these are just recall these three constructions. Okay, so we are interested in pattern preserving quasi-isometries of the Heisenberg group. So what are the patterns? This HX consists of this kind of matrices where the y and the z coordinates are 0. So this is just the x-axis. It's one-dimensional subgroup of the Heisenberg group. And to consider all their left cosets. Okay, so this is the set of left cosets of HX. Similarly, we can consider y-axis, which is also one-dimensional subgroup, and their left cosets. And this H is the union of HX and HY. So you can see all the cosets of x-axis and the cosets of y-axis. So that's the patterns that we're interested in. An affine map of the Heisenberg group is the composition of an automorphism and left translation. So the main result is the following. So we start with quasi-isometry of the Heisenberg group. Now suppose there's a constant d such that for each left coset of the x-axis or the y-axis, its image is at half of distance at most d from a coset of x-axis or y-axis. If that is true, then the quasi-isometry F is at a bounded distance from an affine map. So as we saw from the previous constructions, the quasi-isometries of the Heisenberg groups are very flexible. But if they preserve this kind of structure, this kind of pattern, and it is quite rigid. It's bounded distance from an affine map. So here I gave the statement for the x-axis and y-axis, but it's true when the x-axis and the y-axis are replaced with other one-dimensional subgroups whose projections on a pi are linearly independent. Similar statements also hold for the higher Heisenberg groups and the discrete Heisenberg groups.
Sorry, excuse me, Xiangdong?
Yeah.
So I'm trying to remember what Richard Schwartz did with complex hyperbolic space, right? He has these pattern rigidity results where you take a lattice, right? You take a lattice and look at like a geodesic whose orbit gives you a discrete family of geodesics, which is lattice invariant. And then you look at the quasi-isometries, which preserve that family. I may be misremembering. Is that and then he shows that they're bounded distance from an isometry. Is that, have I got that right?
It's similar the similar in spirit. Yeah.
Okay.
Yes, okay, I see more why we consider this kind of quasi-isometries. Yeah. So the reason we consider this kind of quasi-isometries. So this pattern preserving quasi-isometry arises naturally if you study quasi-isometries of graph groups where the vertex groups are discrete Heisenberg groups and the edge groups are infinitely cyclic. This is so-called JSJ decomposition. Okay, so instead of recalling definition of graph groups, let's just look at one example. So consider a compact manifold, which is the quotient of the Heisenberg group by the discrete Heisenberg group. The x-axis, y-axis project two circles in this manifold. Okay, so I don't know if you have to assume this. You can assume the circles are disjoint by just considering a projection of a coset of the y-axis instead of the y-axis. Right? Now, you take another copy of the manifold M tilde with circles Cx tilde and Cy tilde, and glue them together by identifying the circle Cx with the circle Cx tilde and Cy with Cy tilde. Now consider the universal covering space X tilde. Now, since X is the union of two copies of manifold M, so the universal covering space is the union of copies of the Heisenberg groups. They group together along cosets of the x-axis and the y-axis. Now you consider a quasi-isometry of X tilde to itself. Then here you can apply a theorem of a subgroup, which implies that F sends copies of H to bounded distance from copies of H. Now, if you restrict the quasi-isometry to a copy of H, then we obtain a quasi-isometry of the Heisenberg group that preserve the pattern. That's the assumption in the theorem. So this assumption arises naturally when you consider quasi-isometries of graph groups where the vertex groups are discrete Heisenberg groups and edge groups are infinite cyclic. Okay, so the proof of the theorem let's denote the xz plane by hxz. This is a subgroup of the Heisenberg group. Now, there are a few simple facts that you can check by direct calculation. Two cosets of the x-axis, they are at finite Hausdorff distance from each other if and only if they lie in the same coset of the xz plane. Now, if you consider any two cosets of the x-axis, you fix one of them, you travel along the other coset, they always diverge sublinear. So any two cosets of x-axis diverge sublinearly. Now you consider coset of the x-axis and the y-axis. You fix one of them and travel along the other one, and then they diverge linearly. Now we consider quasi-isometries. So the linearity, sublinearity, and finite, these are all preserved by quasi-isometry. So we start with the quasi-isometry of the Heisenberg group and assume that it sends coset of x-axis or y-axis to a bounded distance from a coset of x-axis, y-axis. Then, by using 2 and 3, the facts 2 and 3, we may assume that all the cosets of x-axis are mapped to finite distance from a coset of x-axis by composing an automorphism of H that switch the x-axis and y-axis. And by 1 and 2, fact 1 and 2, we see that if L1, L2 lie in the, so let's see, this is the coset of x-axis, L1, L2. If they lie in the same coset of the xz plane, then, okay, this L tilde notation case. Then L1 tilde and L2 tilde also lie in the same coset of the xz plane. And same for the coset of y-axis that lie in the yz plane. So the corresponding L1 tilde, L2 tilde also lie in the same yz plane. And the coset of yz plane, that's right. Okay, so that's the simple observation we need. Now, we're going to modify the quasi-isometry F. For each point P in the Heisenberg group, we let LPX be the coset of the x-axis that pass through the point P. And similarly, LPY is the coset of y-axis that pass through the point P. By our assumption, the image of LPX on F is at Hausdorff distance at most d from a coset of x-axis. Now it is denoted by LPX tilde. And similarly for the image of LPY. Okay, by choice, these two cosets, the LPX, LPY, they both pass through point P. However, in the image, this LPX tilde and LPY tilde, they may not intersect. So actually, if these cosets tilde, they are not uniquely determined. So you can shift a little bit in the vertical direction, the central direction, it still be okay. So these are not uniquely determined. So there's no reason to believe that the LPX tilde and LPY tilde would intersect. So in general, they don't intersect. So here we modify a little bit. F1, so we have F1 and F2. So F1 will be the intersection of this LPX tilde with the coset of the yz plane that contains the coset of LPY tilde. So they intersect, and we map F1, map P to this intersection point. Okay, so with this modification, so F1 is still quasi-isometric. Now, it has additional property that for each coset of the x-axis, L, its image is also a coset of hx. Now, it's not just at finite distance from a coset. It is exactly a coset of the x-axis. However, we cannot arrange this to be true for both x-axis and y-axis. So in general, the image of coset y-axis on F1, they are not necessarily a coset of the y-axis. Now, if you take a closer look at the construction, the F1 image of coset of the xz plane are exactly coset of xz plane. And same for the F1 image of the yz plane. So that means there are functions let f little g from R to R, and a function h1 from R3 to R, such that this map F1 has the formula. So F1 sends x, y, z to delta fx, delta gy, and h1 xyz. So the image of the point, the x coordinate of the image point depends on the x coordinate of the point, and the same for the y. But the z coordinate depends on all three coordinates. Okay, that's for f1, but we can modify the map f in slightly differently. So we can consider the intersection of the y coset, LPY tilde, with the coset of xz plane that contain the LPX tilde. Then, so this is similar to f1. So f2 has the property that which coset of y-axis its image on f2 is again a coset of y-axis. And similar to f1, f2 has the formula. The first two components have the same formula, but the third coordinate could be different. Okay. As f1 is a quasi-isometry, it's easy to check that. So the formula for f1, you see that induce a map from R2 to R2, which is given by letter f and letter g. It's easy to see that since f1 is a quasi-isometry, induced map is also a quasi-isometry. Okay, so this is the like. So you want to talk about rigidity here. So if in general, if you start with two quasi-isometries of the line, so f1, g1, then the product map is also a quasi-isometry. So there are lots of quasi-isometries of the line. So that gives you lots of quasi-isometries of R2. However, in our case, these two maps, little f, little g, comes from the quasi-isometry of the Heisenberg group. So in the Heisenberg group, there are interactions between the x direction and y direction. So it turns out that for f1 to be a quasi-isometry, the two maps, delta f, delta g, must be linear functions. Okay, to see this, we rewrite the two maps f1 and f2. The reason we rewrite is that the current formulation, the formula expression for f1, this doesn't tell you that the image of x, the coset of x-axis on the f1 are cosets of x-axis. So we want to rewrite this to reflect this fact that f1 sends coset of x-axis to coset of x-axis. Okay, so for this, we work on the algebra using the usual basis x, y, z for the Heisenberg algebra, which satisfy the Brecht relation that the Brecht of x and y equals z. So now we write the map f1 in this like this. So we consider a point will be written as a point in the y-axis times a point in the xz plane. We know f1 has a property that sends coset of xz plane to coset of xz plane. So it has this formula. So and in the y direction, no, it's given by g letter g, okay? And in the x direction, is given by letter f. But now, instead of the previous formulation where h1 depends on all three coordinates x, y, z, now here h3 only depends on y and z. It doesn't depend on x because f1 sends coset of x-axis to coset of x-axis. So this h3 doesn't depend on x. Similarly, there's a function h4 from R2 to R such that f2 has this formula. Delta x capital X times a point. So this is a point in the x-axis times a point in the y-z plane. And there's h4, which is independent of, so this is independent of y. Now we obtained the two maps f1 and f2 by modifying the original quasi-isometry f. So the distance between f1 and f2 are finite. Now, you look at the expression for f1, f2. See here, the point upon the p is written differently. So you given upon the p, you write differently, like this. So we know that y coordinates has to be the same, or x coordinate has to be the same. But is z here? They are different. We see denoted one of them is denoted by z1, the other is z2. And you calculate directly this relation between z1 and z2. So z1 equals z2 plus xy. Now we know there's constant c such that for any point of p, the distance between f1p and f2p is at most c. Now, using the expressions for f1 and f2, we get this. So this is similar to the expression z1 equals z2 plus xy. But we have this equality because p has these two expressions. But for f1, f2, they are not, they don't agree. I mean, they don't agree, but they're at distance at most c from each other. So this inequality is similar to this equality, but no. So this is so h3 is in position with z1, h4 is in place of z2, and fx is in place of x, gy is in place of y. So this equality becomes this inequality. This is true for any x, y, and z2. So now you just work with this inequality. So now you look at here, it's true for any x, y, and z2. So you take some special values for x, y. So for example, you can, by applying a left translation, you can assume f0 equals 0. And you in this inequality, you set x equal to 0, then the distance becomes 0. So you have h3y z2 minus h4 0 z2 is bounded from above by constant. That's true for any y and a z2. And by doing that, so we can deduce that the two functions, letter f, letter g, are linear functions. So you still have to do something, but it's just it's easy. It's elementary. So once you show that letter f, letter g are linear functions, you can see that the quasi-isometry is bounded distance from an affine map of the
So may I ask a quick clarifying question? So you're saying this inequality that you have, right?
Right.
So you don't need any other properties, just this inequality, and you can deduce that f and g are linear?
Yes.
Uh-huh.
Yeah, this is just elementary, but some details to be worked out. So eventually, this h3, h4 will be independent of y. I mean, up to bounded distance. So it's independent of y, independent of x here. So you just erase y here, erase x here, and f will be linear in x, y is linear in y, and h3 it will be linear in z. So you see that this Z2 will cancel out, but you still have this term xy, but that they will cancel out with this product here. Because fx is linear function x, y dy is linear function y. This from here, it's to see little f little j linear function. It is elementary. Should I still have time. That's all the slides are prepared. Sorry, I stopped it earlier. Yeah, and that's the end of my talk.
But so sorry. You
Yeah.
know, in principle, these h functions could just be zero, right?
No, they cannot be zero. Because they have this quasi-isometries kind of onto him.
Oh, I see. So you do need some information about these h functions then.
Do I need? Oh, let's see.
I mean, you're saying that this inequality alone implies that you get linear.
Did I use additional information? Maybe. Sorry. But it's elementary. Frankly, it's an elementary. Yeah, it's just you deduce this by taking you normalize. So first normalize so that f0 equals 0, g0 equals 0. You can do that by applying, composing the quasi-isometry with left translation.
Mm-hmm.
And you take some special values for x equals 0, you get some information here. Y equals 0, you get some information here. So for this one, you see that if you take x equals 0, you need to see that they are independent of the first coordinate, namely the y and the x. So you can see this h3 of z2 plus xy and h4 of z2 by enlarging this constant. Right, so this is just some details, but it's elementary. I didn't include. Okay, so yeah, that's okay. That's probably too short a talk. Sorry.
Okay. Well, so let's thank the speaker. And let me open the discussion. So any comments or questions? Well, so let me ask you a question. So you mentioned the motivation why you wanted to study these type of pattern rigidity results, right? So there should be some kind of obvious applications of this then to maybe some rigidity.
Okay, good question. I was preparing that part. Then I found there's one step I need to be careful. So I didn't include that part. So that shortened the talk.
I see. So this is kind of work in progress.
Yes.
I see. I see. Okay. Are there other comments or questions?
How much does this depend on the Heisenberg group? So can you do anything similar in other Cardinal groups?
That's a good question. This argument apparently doesn't apply in general. So yeah, we're thinking about the general case for the other Cardinal groups. Yeah.
Yeah, as Bruce mentioned, right? I mean, there might be some kind of a general theme here.
Yes, there are in geometric group theory, there are some reasonable work on this kind of rigidity. Yes, so we're inspired by those results.